All right, welcome back. We're going to talk about shoreline levee project on the South San Francisco Bay and some lessons learned from that project. It's been going on for many, many years, and it started and was kind of early project in the kind of geotechnical performance modeling. There were some lessons learned, and the project is ongoing with new phases all the time. But I just thought I'd kind of share some of the lessons learned and some things for everyone to think about, especially the geotechnical engineers. So this is kind of a map of the original project scope area. So this is South San Francisco Bay. On the left side, you have Palo Alto. On the right side is Fremont. And so basically the project, has all these kind of abandoned or decommissioned salt ponds where they used to do salt harvesting from the bay. So the water gets into one pond, gets evaporated, and it cycles around until you end up with a pile of salt at the end. That's been decommissioned for a number of tens of years now and taken over by various agencies, including Fish and Wildlife, the Santa Clara Valley Water District, some's owned by the state. So anyway, but the original project was to provide flood protection and ecosystem restoration from the whole range. And a lot of explorations were done and analysis were done to help design those projects. Some of the very early work, we had problems with the modeling, and we weren't exactly using HEC-FDA. It was a complicated program that was written by ERDIC and run on the supercomputers at ERDIC, but we had problems with datums. We had problems in the model coding, and so there's some key differences in how the Monte Carlo worked there versus how like a joint probability calculation might work. And so, for example, like in a Monte Carlo, you queue a distribution of results and see if something happens. So one of the Monte Carlo questions was, does the levee fail? And so they were queuing it every few minutes, to model a storm event. Does it fail now? Does it fail now? And so, of course, the more you ask it by rolling the dice, it's going to fail all the time. And so rather than just, if a joint probability approach, you'd say, here's the load, here's the probability. And so that had to be kind of sorted. So that was one problem at one time that we dealt with. So be sure you understand how the model works and how the geotechnical system response functions are working in the model. And then at other times we were trying to figure out how do we incorporate length effects versus index points. So we had very long reaches of levee, and was one index point the right way to model that whole system? So there was a lot of difficulties with that. And then there were some questions during the work about modeling probability of unsatisfactory or poor performance versus probability of failure. And so we'll talk about that here more in a second. All right, so to get to the discussion about probability of unsatisfactory performance versus probability of failure, I think it's important to realize that many engineers are kind of conservative by nature, and in our engineering, we want to design things that are reliable and safe, right? So this is one of the early kind of probability curves that we had, that we were working with, and what's wrong with this table that you see there? Okay, this was the probability that we were dealing with for a specific levee. Okay, so I'm gonna let you take a look at that table there for a second, and then we'll move on to the next slide and kind of talk about it a little bit. So there's a couple challenges that we had here, and these challenges are, first, the probability of unsatisfactory performance you see right here in the table. We were looking at probabilities of the factor of safety is less than 1.1. And that seems like, oh yeah, that 1.1 is a very low factor of safety. But what we really want is the probability that the factor of safety is less than 1.0, because 1.1 doesn't mean failure. It just means we almost got to failure. So we want to be doing everything for a 1.0 kind of calculation. Now, this is counterintuitive to many engineers, but it's important to do that during the risk calculations because we're evaluating risk and we're not necessarily doing new designs. Okay, so just because we design it for we evaluate it for a factor of safety 1.0 in the without project doesn't mean that we're designing it for that. That's just to evaluate and understand the risk. Okay. The second thing, and that is we can see that we have this sketch on the left showing different failure slip surfaces that were evaluated, and each kind of different geometry has its own probability of occurring. Well, we need to pick one that fails the levee. So in this case, why are we looking at shallow failures, half levee failures? We need one that fails the levee. So that's why this arrow here is. This would be the more appropriate, most appropriate probably for this situation is the full levee width and calculating the probabilities of failure for a factor safety of 1.0. And then the other thing to note is this is just the limit state for is the strength of the levee going to be exceeded. And we still need to evaluate the loading, hydraulic loading, if the conditions that we modeled are actually there, okay? And if the load and the progression of the failure is actually going to lead to breach. So all those nodes should also be considered in determining the probability of failure, not just the probability of poor performance. All right, so one other lesson that we learned early on in the shoreline project is that there can be kind of confusion about variability and uncertainty and how those are kind of incorporated in geotechnical engineering. And so if you're an earthquake engineer, you probably have heard of aleatory variability and epistemic uncertainty a lot and understand what we're talking about when we talk about those, but it sometimes can make a difference and sometimes important to think about. So when we talk about aleatory variability, what we're talking about is randomness of process, okay? So like if we have a certain material unit, we say, yeah, we measured the strength to be something, but we don't really, there's some variability and randomness in our measurement, like it's not perfect, right? So well, we don't have perfect measurements, we don't really know, so it might range from some number to some other number, okay? The epistemic uncertainty is really about, do we have the model right? So we have modeled a levee with certain soil layers. Is that model right? Okay, or is it a different model that we should be using for maybe different soil layers, or maybe there's something that changes the model, not just as a variability in the model. Okay, so those are kind of the differences. And I'd like to illustrate the point here with these two plots. If you look at the top and you kind of see these, black and white, and all these points are equal, you might plot the average strength of this material with this blue line on the top plot, okay? And that's sort of not really the correct way to do it, because when we look at the data more closely, we see, I plotted in color here to make it more clear, this yellow line of data all comes from one location, and all has a lower strength than this other more random data. So if we were modeling a weak point, we wouldn't want to model an average strength up here with some possible range on it. We want to model this low strength situation here with some variability on it that that it could range from. But this top one would be the incorrect model to use, and we need to identify the weak point and then model the weak point directly, okay? So this would be an error in modeling, and so that would be an epistemic uncertainty. Here we can resolve it, but that's kind of the difference, right? We have different models of how we might do that. And then the range on this yellow data, that would be our aleatory variability for geotechnical modeling. All right, we're gonna go on. So here's kind of what we talked about, and exceedance probability, determining if the results are reasonable, sources of unreasonable results, and we used shoreline to talk about some common problems and make people aware of them so that they can be handled. So with that, I'll ask, are there any questions? If there are, you can reach out to me at the Dam Safety Production Center in the South Pacific Division. Thanks a lot. Bye.